Go ahead and get started. So I think, John, we're going to start with you.
Yes, hello everyone. Welcome to our ECOG session on engineering your future. Today we have three speakers with us. First we have Dr. Lynnane George, who is a professor at University of Colorado Springs. She's a professor in Mechanical and Aerospace Engineering. We have Dr. Michael Calvisi, who is also in the Department of Mechanical and Aerospace Engineering at UCCS. And last, we have Sgt Sweet, who has her bachelor's degree in aeronautical engineering and works in the United States Space Force. And with that in mind, take it away.
Okay, thank you all for coming to this session. I have been looking forward to it for a long time. I usually do these educating children of color every year that I can possibly participate. Unfortunately, well, I guess fortunately and unfortunately, it's online this year, but we do have some fun activities for you. My background, like John mentioned, is I'm a professor at University of Colorado Springs, and I spent most of my career in the Air Force. So if you ever wonder what engineering is about, I was a mechanical engineer because I learned when I was a kid. How many of you guys are good at breaking things? That was me. And who liked to blow things up? That was me too. So I thought, let me become a mechanical engineer so I can do that for a living. So I actually got to do that. Rockets that launch into space are really just controlled explosions. So it's a fun career to get into. You can do some hands-on stuff. And now I'll turn it over to Michael.
All right, thank you. Well, I'm happy to be here, and hopefully there's not too much of a delay in my video. But anyway, I'm an associate professor in the Department of Mechanical and Aerospace Engineering, same department as Dr. George at UCCS. So my background is I got my bachelor's degree in mechanical engineering, and then I worked for about 7 years in industry. And then after I stopped learning, I decided I wanted to go back to school. And then so I went back to school at UC Berkeley. I got my master's and Ph.D. and then went about becoming a professor. So I landed at Colorado Springs, and my main area is in fluid dynamics, so which is a very broad field. So any liquids or gases are considered fluids, and it has broad applications, for example, to studying aerodynamics of vehicles or weather prediction, to just about everything in between. But my particular interest is in studying bubbles, especially microscopic bubbles, and using them for doing drug delivery. So I'll talk a bit more about that later, but we are able to use microscopic bubbles to deliver drugs within the bloodstream and to fight diseases like cancer. And so this is something you might not think a mechanical engineer would be involved in, but actually it's really based on a lot of the fundamentals that we learn as mechanical engineers, which mechanical engineering in its broadest sense is really the generation and conversion of mechanical energy in order to do work. So it could be anything from generation of, say, heat, propulsion, any kind of mechanical systems, anything that essentially moves. So robotics, cars, planes, trains, automobiles, those are all designed and by mechanical engineers. So, so anyway, I'm excited to be here. I'll tell you a bit more about my research and what we're doing. And I'll turn it over to Sgt Sweet, who will introduce herself.
Hello everyone, I am Sgt Sweet. I am currently active duty with the Space Force in Colorado. This is my first ECOC that I've ever attended, so I'm super excited to be here. Not only to teach you guys some things today, but also learn from this experience myself. My background in STEAM, or as it was called STEM, is pretty reliant on my time or my career in the military. I was Air Force for 3 years and I've been Space Force for 1 year. A lot of space assets is kind of where my knowledge lies, but today, going through biomedical engineering, helping you guys learn some stuff about that, I actually learned some stuff too. So I've got a very long way to go in my career in aerospace engineering as I'm transitioning into it currently. So that's all I have for you. I'm excited to be here.
Thank you all. All right, so we're gonna start off by making this a little interactive, or hopefully a lot interactive. And I'm gonna start off by asking you guys, and you can put it in the chat if you'd like, or you can raise your hand and I'll call on you. But first question, what is engineering? How would you define engineering? So what do you guys think? So again, you can type it in the chat, or you can raise your hand and speak up, either one. Or if no one does, I'll call on a few people. So what do you think engineering is? I'll be quiet. What is engineering? To me, engineering is putting something together. That's from Godwin. Okay, good. Alicia, I hope I pronounced that right. Making things mainly with electronics. Okay. Marquise, something to do with math. Yeah, that's true too. That is a necessary part. Engineering is the process of building and creating new things. Yes, very much. Without engineers, we wouldn't have things ranging from computers to automobiles to cool things that you can do with your phones and your technology. The process of making something to make life easier. Yeah, that's definitely one. Walking is a lot harder to do than riding in your automobile, your car. Finding solutions to problems. Yes, that's good too. Working with mathematical processes to create things and solving problems with math and science. We also have creating and making things easy. So all of those are very good definitions of engineering. So more specifically, what might biomedical engineering be? What might biomedical engineering be? So in this case, Zaya says, taking research that scientists have gathered and applying it to solve problems. What type of problems? Ariana says, creating new cures and medicines. Absolutely, or better ways to get those medicines to people to help them feel better, or to help them heal. Absolutely. Using natural resources to attack medical issues. Biomedical engineering is making equipment for the medical field. Yes, all of those are very good definitions. Thank you for all of the participation in the chat. Making equipment for the medical field. Protecting and creating medicine. Yeah, so we're going to talk about all of that. Any other last thoughts, or Dr. Calvisi or Sgt Sweet, would you like to add anything to that?
No, I think those are a lot of good ideas. I think those are right on. Basically taking the principles of engineering and trying to cure diseases and help people with medical problems. I think that's probably the broadest definition I can think of. Do you have anything else, Anna?
The only thing I'd add to that is definitely just breaking down the word, right? Bio to be life, medical obviously to be like dealing with medicine, and then engineering. So you're engineering medicine to better life is how I like to think of it. That helped me remember.
Absolutely. Thank you all for your inputs here. Okay, so what we're going to do today, this is a boring slide, so I'm not going to spend much time on it, but mostly what we're going to do is show you some things that you can do at home to help you learn about various engineering concepts, and to help you, we're going to finish it up by introducing you to a game that you can play at home. I will give you access to that, and that will teach you more about biomedical engineering. So with that, Anna's going to talk a little bit more about biomedical engineering.
So biomedical engineering, as I very briefly mentioned, when we break down the word, it's bio, medicine, and then the engineering aspect. Biomedical engineering is like, we had some really good answers in the chats, right? We had a lot of understanding that it is finding a problem to a current solution. And in this case, those problems are going to be medical problems. It can be anything from sicknesses to, as Dr. Calvisi mentioned, it could be cancers to stuff like amputees, right? Biomedical engineering can be the design or the engineering of prosthetics. And that's what we're seeing a lot in current science. So it's everything from the physical aspect to the chemist aspect, right? So the chemicals that you're needing to figure out what is going to react with people's brains. It could be anything from solving psychological issues, right? People with depression, people with anxiety, ADHD. Somebody sat down, realized that that was a problem in medicine, wanted to make someone else's life better, and then engineered the chemicals that needed to be engineered for that. As we see future technologies with biomedical engineering, we're seeing a lot of incorporation in robotics. That's pretty huge. And then we're also seeing biomedical engineering in not just humans, but obviously with animals too, right? If your dog gets sick, if your cat gets sick, if your horse gets sick, or loses a limb, et cetera, biomedical engineering is also applied to the veterinary sciences as well.
Okay, are you ready for your demo?
I am so ready. So this is one of my favorite experiments to do, and I actually learned this experiment for you guys to do at home. So this is going to be about bubbles and something called surface tension. So we're going to get rid of the boring aspect of things, right? So go through the science real quick. Can anybody, if anybody knows, what do they think surface tension is? If someone could get into the chat with that. It's a very kind of a difficult question, but if anybody thinks that they know.
Would surface tension be like how hard or soft an area is or something is?
So that's really, really good. So you're on the absolute right track. So in this case, what we're talking about is we're talking about the surface of water specifically. So when we talk about things being hard or soft, we're talking about what they're actually made of and like molecular breakdowns. For this one specifically, we're talking about the surface of liquids, right? So surface tension on the surface of liquids is the phenomenon that makes things float. That is the simplest that it can be put. So what we're looking at today, as Dr. Calvisi mentioned earlier, in biomedical engineering, there is a new technology in which you're taking a bubble, you're filling it with medicine, you're sending it through the human body, and it's going to get to where it needs to go, and then it's going to release the medicine in certain areas. One of the things we're going to be looking at is bubbles, right? We're going to be looking at how bubbles react when they're on a liquid surface and why they don't pop. That's because of that surface tension. So super easy experiment that everyone can do from home. There's only a couple of ingredients that we're going to need. The first is going to be standard dish soap. Most people have this. The second is going to be straws. Any kind of straws will do. These are some of my favorites. They're called sustainables. They're eco straws that you can buy at Walmart. So they feel like plastic straws. They work like plastic straws, but they're more compositable than that. We're going to take warm water, mix it with our dish soap. You do a cup of water with 1/4 cup of dish soap. You can also get something called glycerin, which you can buy at the store. Not a lot of people have this in their house. It'll work just with dish soap and water. If you want to get glycerin, what it's going to do is it's going to make the shell of your bubble stronger, so it actually pops less easier than it would if you didn't have it. So for me, I want to experiment with what most people have, so we're just doing dish soap and water solution for our experiment today. Then you're going to want a spray bottle with water in it. This can just be water from the tap. The spray bottle that I have, I just reused from some hair products that I had in my house. So if you don't have an empty spray bottle lying around, but you've just run out of any kind of maybe some Windex or something of that sort, then you can just rinse that out, fill it with water, and then use it that way. And then of course, this is going to be a messy experiment today, so you definitely want some paper towels. I've also got mine here, and then a surface that you can wet down. So the surface that I have today is just going to be my glass tabletop. You're going to take your bubble solution, your straw, which I have, and we're going to try this experiment without wetting our tabletop first. That's eventually what we're going to do. So you're going to put your straw into your bubble solution. And then when you take it out, if you just want to drip the remaining water just a little bit so it's not dripping everywhere, and then you're going to blow through your straw, through this end of the straw, and it creates bubbles. Now, as you see, when the bubbles hit our dry surface where we don't have any liquids, so we don't have any surface tension here, they're going to pop, which when they pop, they're actually evaporating. So when we look at surface tension, we talk about things floating and we're looking at the actual bubbles themselves. Let's see what happens when we actually wet down our surface. So we're just going to do a few sprays. You don't need a whole lot here. You just need a little bit of water, just a very thin layer of water on your surface. So now when we take our straw and we put it into our bubble mixture, again, we're going to drip off some of that excess. I think I blew a little too hard. So just very, very, very soft breath. Our bubble didn't pop. So our bubble is sitting on that layer of water and it's using that surface tension to not evaporate. So when we talk about the actual bubbles that are going through the body and going through the system to release medicine, it's very similar to this, right? The difference is with biomedical engineering, we've actually engineered the outer layer of that bubble to be even more resistant in the human body so that it can get to where it's going without popping too soon. So we put definitely our layer of bubble, and then inside that bubble, we've actually put more layers. So what that's going to look like if you wanted to do it at home. You can actually put the bubble inside the bubble. I messed up, my bubble wasn't big enough, but you can definitely experiment this at home. It's a very easy experiment to do. And then again, if you experiment it with on a dry surface versus on a wet surface, and see actually how big your bubble can get or how many bubbles that you can put inside of those bubbles.
Okay, thank you, Anna. All right, so I'm going to turn my camera back on and we're going to do another demo. And again, this is one that you can do. And I'm going to share my screen here. Let me go back to share screen. And I am going to do a little demonstration here of some basic noise principles. So what do you see? Can you guys hopefully see my camera? What do you see here? Can anyone tell me what you see here? It's pretty basic, pretty simple, something that you can have around the house, basically. What do you guys see here? What have I got? What is this? Anyone want to guess? A glass of water. Yay, we got a winner there. All right. Yeah, so it's a glass of water. But the interesting thing is I can use that principle of water and create what's called vibrations. And this is going to be necessary for what we're going to do later. We're going to talk about frequency. So here, all I have to do, can you guys hear that? All I have to do is rub my finger around the outside of this glass here and it makes a noise. So I can do that with any of these glasses, really. Makes a very high-pitched sound. So what we're going to do is look at what's called the frequency of those. And does anyone know what frequency means? What does frequency means? I am a junior at Mesa. What should I be saying? Okay, yeah, we'll get to that for a few minutes. Good question from our keys. H2O, water. Okay, so far we've talked about that. Now, what this is called a spectrum, which gives you different frequencies. So do you guys know what frequency is? Can anyone give me a definition or just what you think about when you think about frequency? Have you ever heard the term frequency? Or you could just type no if you haven't, or you could type yes. how high or low a sound pitch something is. Yeah, pitch is a good way to think about that. Low, how high or low something is. Yeah, absolutely. Yeah, so these are all pretty high pitch, but they're still in our frequency range. So let's see, and you can see as I'm talking, there's different frequency components. What this is plotting is the main frequencies. Frequency is across the bottom of the graph, and then how strong that frequency is on the vertical graph. So let's see, look closely and see if you see anything highlighted when I start making the glass sing. Did you guys see that frequency right around the middle, right around that red line? Around that red line, that meant that frequency was mostly predominant at around that red line. So let's just take a note of that. That looked like that is about pretty low, maybe a couple of hundred hertz. Hertz is cycles per second. Let's take a look at a different one. Now you see that one was a little above that red line. This is a larger glass with a little less water. So you can see one to the left of the red line, a big one right to the left of that red line there. So that is called a lower frequency, lower pitch. And now look closely at this one. Let me move some of these others out of the way. This can really show frequency at right around that line, right in between the purple and red. And that is a little lower pitch frequency because it has more water in it. So what I encourage you to do is take some glasses. Wine glasses work best, but if you don't have those, that's okay. Take some different glasses, put water in it. All it takes is your finger, get your finger wet, and you just move your finger around the outside of the glass and it sings. It's called singing glasses. So what I'd like you to do is, if you can look a little closer up, you can actually, this water has been sitting out for a while, you can actually see some of those bubbles vibrate. You kind of see the one in the bottom, it vibrates a little bit, which is really hard to see on this camera, but it does vibrate a little bit. And that is what we're going to be talking about in a little later in today's session, is how frequency relates to drug delivery that Dr. Calvisi is going to talk about. Basically, the bubbles have their own frequency at which they vibrate. So this, what I had here was the natural frequency of that glass water. So that's where it tends to naturally have its tone or its pitch. Now, when I move to different glasses, that pitch changes. Well, you've probably seen videos of an opera singer singing really high pitch and like breaking all the glasses. It's really cool demonstration, but it breaks those, can break those glasses. Dawson put in, fun fact, human hearing fixates on the range 200 to 4,000 hertz over most frequencies. Yeah, so we can only hear over a certain number of frequencies, maybe a little more than 4,000, but definitely no longer than 200. And an example of where it's outside of our hearing, if you've ever seen or heard those dog whistles that make the dogs go crazy, but you don't hear them at all, that's because it's at a higher frequency than we can hear. So we're going to use that in our research today to show you how drug delivery happens, because it's like one bubble will get near another bubble that vibrates at the same frequency, and it can do just like what the opera singer does to the glasses, and it can make those glasses burst. So I encourage you, it's really fun. I have glasses all over the place with water in them. I like to see how many different noises I can have them make. And it's just a fun thing to do that you can do from home. So that was my demo. Let me go back to our slides and turn it back over to Michael Calvisi. Let's see, let me go back to where we were. I think we were right here. Okay.
I think slide 7, marvels of medical microbubbles.
Oh, that one. Yeah.
Okay.
There we go. Back over
Okay.
to you.
All right. So thank you, Anna and Lynnane, for those demos. So that will lead into my presentation here. So it's on the marvels of medical microbubbles. So it's a mouthful. We'll break it down here. If you could go to the next slide, please. So really what we're talking about is new therapies for treating cancer as well as other diseases. Imagine you probably know someone who's been affected by cancer. It's very common. So what is cancer? It's a group of diseases involving abnormal cell growth with the potential to invade or spread to other parts of the body. So it involves, so there in the diagram on the right there, the normal cells are light colored and the cancerous cells are blue, and they tend to divide and grow at an abnormal rate and form tumors. In addition, they can spread to other parts of the body, and they can form in any organ. So the liver, lung, pancreas, so forth, brain. They can also what's called metastasize, which means they can spread to other parts of the body and form. So if treated early, cancer often is very treatable, but if it goes unchecked and the tumors get too large, then it can cause serious illness and death. And in the United States, and these statistics are a little bit old, but I think they're still roughly accurate, people have a 1 in 3 chance of developing cancer. So this is men and women have a 1 in 3 chance of developing cancer and a 1 in 5 chance of dying from cancer. So it's one of the leading causes of death. And approximately 14 million people are living with cancer currently. And the medical costs associated with cancer, and this was in 2015, so I imagine it's probably higher, but in 2015, the medical costs were about $80 billion. So it's very expensive to treat. So if we can come up with more effective ways of treating cancer, we can both save money and save lives as well. And so that's what this research is about. If you could go to the next slide, please. So there are different methods of treating cancer. There's no single cure. It depends on what organ it's forming in. It also depends on the stage of development. But one treatment for cancer is called chemotherapy. And chemotherapy is essentially a drug that gets delivered to the body, and it's very toxic for cancer. So it's very effective at killing cancer cells, but the problem is that it's also toxic to the rest of the body. And so when we use chemotherapy, it's sort of like using a shotgun approach. We take out the cancerous cells, but we also harm a lot of other good, healthy cells as well, which we'd rather not do. And so chemotherapy is usually delivered by intravenous infusion into the veins. So where you have essentially you inject a needle into the veins and you deliver a liquid into the veins. It goes throughout the entire body. Some of it gets absorbed by the tumors and the cancerous cells, but healthy cells also absorb the chemotherapy, which is toxic. Can also be delivered through oral pills or liquids, as well as through shots into the muscles under the skin. So systemic delivery causes a number of negative side effects. So one of them is nausea, also fatigue, immune suppression, hair loss. Also the fact that it goes throughout the body and essentially poisons the body. It limits how much can be delivered at any one time. So it forces us to, so rather than say doing a single chemotherapy treatment to kill the cancer, we're limited to only delivering a certain amount at any given time. So usually chemotherapy has to be delivered over very many treatments over weeks or even months, which delays the benefits of the chemotherapy and limits how rapidly we can deliver it. So if we can find a way to deliver the chemotherapy in a targeted way just to the bad cells, the tumor cells, without affecting the good cells, that would improve the treatment and allow us to save more lives and also reduce the medical costs that are associated with it. And so that's where microbubbles come in. So microbubbles are a way to deliver chemotherapy in a targeted way to cancerous tumors. So if you could hit the return and then go to the next slide, please. Yeah, so microbubbles are the solution here. And we're not just talking about any bubbles, the types of, so Sgt Sweet showed some demos with bubbles. So these are similar in a way in that inside there's a gas and surface tension is acting on the outside, but there's this special engineered shell that helps to keep the bubble intact and keeps it from dissolving. So the way this works is these bubbles are injected into the bloodstream. So usually they're in a solution of some sort of liquid, and they have a special gas, not the type of gas that you would breathe or ordinarily find, but it's a special gas that doesn't dissolve very rapidly. And it has an engineered shell, which is usually made of a solid elastic material. So it could be a protein or it can be a lipid, which is like a fat, but it has to be elastic so that it can vibrate. And these bubbles are very small. So when you say micro, that is short for microscopic. So these are on the order of 1 to 10 microns in size. So to give you a sense of the scale, human hair, if I were to pluck a hair from my head, is about 100 microns. So these bubbles are about 1/10 to 1/100th the diameter of a human hair. And so they're very small. They're too small to see with the naked eye, but they're small enough that they can pass through all of the blood vessels of the body without blocking the blood vessels, because that would obviously be very bad. And the shell allows them to last for several minutes so that they can get to their target site. If we were to remove the shell, the bubbles would dissolve very quickly. And the figure in the lower right just shows the difference between an uncoated and a lipid-coated bubble. An uncoated bubble, which is the red curve, would dissolve on the order of a few seconds, or maybe even less than a few seconds. Whereas when you add a lipid coating, for example, the green curve, the bubbles can last for several minutes, okay? And in the figure on the very bottom in the lower left, what we do is we apply ultrasound. So ultrasound is sound that is above the range of human hearing. So we can't actually hear it with our ears. A dog might be able to hear it though. So these are oscillating very, very rapidly. So rapidly that we can't hear it, but these are on the range of these are at a frequency that causes the bubbles to vibrate and to increase and decrease in size. And as they increase and decrease, okay, they help to emit sound waves. And that was the original purpose, is that these bubbles were engineered to help out with ultrasound imaging. But we are using them more recently. We're looking at using them as a vehicle for delivering drugs. So if you could go to the next slide, please. I'll talk a little bit more about the applications of these EMBs, or encapsulated microbubbles. So the original application was for ultrasound imaging. If you could click on the figure on the upper right, ultrasound imaging. Thanks. So that actually shows some blood vessels that are highlighted due to microbubbles. So if you didn't have microbubbles, much of the ultrasound, which are just sound waves, would pass right through our body because we're mostly water. But when you add the microbubbles, they help to scatter and reflect some of the sound, and they help to improve contrast. They help us to see what's happening inside the body. They help us to visualize the blood vessels as well as organs. So they're very good contrast agent, and that's what they originally developed for. And this was in the late 80s and early 90s they were introduced. So they've been around for at least 30 years for ultrasound imaging. But in the last, say, 15 years or so, people have started using them, or at least doing research on using them for doing drug delivery. So for example, if you look at the figure on the lower left, you can load up these bubbles with drugs, and they can be in liquid form or they can be in solid form. And when they get to the site of interest, so for example, you're trying to treat a cancerous tumor, when they get to the tumor, you deliver the sound waves, you apply a very strong burst, and it can cause the bubbles to rupture and release the medicine locally. So the idea is, rather than delivering the chemotherapy in sort of a shotgun way where it goes throughout the entire body, we can target it so that we deliver it and release it only where we need it, where the cancerous tumor is. So we can use lower doses overall, which reduces the side effects. And by releasing it where the tumor is, we can help it, the medicine, get into the tumor and kill the tumor cells, which is what we want. So that's the basic idea. So we're using the bubbles as a delivery vehicle, and then using the ultrasound to cause the bubbles to rupture on demand and release the medicine. So these bubbles can also be used for other types of therapy in addition to treating cancer. They can be used for treating, for example, Parkinson's disease or Alzheimer's disease in the brain. It's very difficult to get drugs into the brain because of what's called a blood-brain barrier. The brain is very good at keeping out foreign objects, foreign viruses or bacteria. But by applying the ultrasound, it helps to open up the pores of the blood vessels and helps medicine get into the brain. So this is a potential treatment for treating Alzheimer's and Parkinson's. It can also be used for gene therapy, so using genetic material to treat diseases. And also, this is a big word, thrombolysis. Lysis means breaking, and this is a way to do tissue destruction. For example, as we age, we tend to get hardening of the arteries. We get plaque buildup, which is a hard, sticky substance. And by using the microbubbles, you can use the action of the ultrasound and the microbubbles to essentially mechanically break up plaque or other tissues inside the body. So these bubbles are basically a way to do surgery non-invasively without having to do any incisions other than just injecting the bubbles. The way to do essentially do drug delivery as well as surgery inside the body non-invasively. And this is still under development. In some cases, they are being used clinically for treatment, but researchers are still trying to study these bubbles. And so what I do as a mechanical engineer is I develop computational models of these bubbles. So this is related to my field of research, which is computational fluid dynamics, which is where we use big, powerful computers to simulate fluid dynamical systems. And so, for example, this is used for designing cars as well as aircraft for example, to make them more aerodynamic. We can also use them for understanding the interaction of sound with bubbles in blood. And that's essentially what I do. So I have a grant currently from the National Science Foundation to study this. And if you could go to the next slide, please. So in summary, encapsulated microbubbles hold great promise for medical therapy as well as diagnosis. So as part of my grant, I'm doing outreach to try and educate people about the use of medical microbubbles. And so what I did is I've been working with our computer science department to develop a game. So this is an online game that you can play at any time. We'll show you the link, which is a fun game, which helps to educate you about the use of microbubbles for treating cancer. Okay, so if you could go to the next slide, I'll try to go quickly about this. I have about 5 minutes left. So So I'll talk about the development of the educational game. And so can I, yeah. Let me share my screen here. So educational games are a way to teach people about things in a way that's fun. And so in working with the computer science department, they suggested this game Descent 2, where you're navigating a ship through a maze, three-dimensional maze, and you're shooting at things. But the idea here is that rather than driving a ship, you're driving a bubble through the circulatory system, through the bloodstream, to deliver bubbles to cancerous tumors. So if you could go back to the slides.
You have to stop sharing yours.
Oh, okay, thanks.
Okay. So you do have a question in the chat if you want to answer that while we're transitioning. It says, oops, I just saw it. From Alicia, is it possible the bubble could go in a different direction of where the cancer is?
Sure. So the bubbles go throughout the entire circulatory system, but the idea is you only apply the ultrasound where you want them to rupture, and that way you only release the medicine where you need it. Now, eventually the bubbles will kind of dissolve on their own, and then they'll just get removed naturally. But so some of the medicine will go elsewhere, but by using the microbubbles, you can use much lower doses than you would normally. So you reduce the overall side effects. So I just have a few minutes, if you could just go real quickly through the next couple slides. So the idea is the circulatory system is a maze, and you're navigating a bubble through the maze, and you have the arteries and the veins. If you go to the next slide. And so you have a first-person view of the arteries and veins. So it's as if you're driving a microscopic ship, which is driving a bubble through the circulatory system. Please, the next slide, please. And yeah, so this is the game development team here. We actually have a program within computer science on game design and development. Game design is a huge field. It actually brings in more money than all of sports and television combined. The video game industry brings in more money than all sports and television combined, I'm told. Dr. Wortman is who's the lead developer. She's an instructor. And then these are the various students who worked on it. So these were undergraduate students getting the bachelor's degree. If you could go to the next slide. So the last slide just shows so this is shows the link at top, and this shows the landing page. And if I could share my screen again, I'll just show okay, thank you. So let me go to, so this is the landing page here, and this shows the website here. So it's sites.google.com/view/remission possible/home. Hopefully we can provide that for you. But the name of the game is Remission Possible. So it's sort of a play on the movie franchise Mission Impossible, but remission is when the cancer is receding or shrinking, it's in remission. And so there's a survey here, which we like you to take out, and a bug report. But if you click on the main link here, it'll take you to the game. It takes a few seconds to load, but you can play it online. You just need a mouse and a keyboard. So you cannot play it on your phone yet. And if you hit play, you can play any level you want, but start at first flight and then go through the different levels. But there's some instructions here, which I'll just skip through, and I'll just show you real briefly.
And Michael, I might need to interrupt. We've got 1 minute yet, and I wanted to make sure that first off, could you post that game site in the chat so everyone has it? And then I've already posted my email, but if you're comfortable with it, if you guys could post your email in case any students have any follow-up questions. You did have one from Ariana about research programs or internships, and yeah, we'd love to talk to you. So I put my email address a little earlier. It's lgeorge2@uccs.edu. And if you need to leave, it's now 2:55. We understand, but I think Michael is going to show you a little bit about the gameplay if you want to stick around and for a few minutes and see what that is.
I did, let's see here. Yeah, there's the website for the game if you want to click on it. And we're constantly developing this game, so it may change over the weeks and months, but I'll also put my email address. You're all welcome to contact me about anything I've discussed or anything about mechanical engineering or biomedical engineering. I'm happy to answer any questions, or about game design. And happy to put you in touch with, if you're interested in game design, happy to put you in touch with Dr. Wardman, who is an instructor in game design. I'm sure she'd be happy to talk to you about that. So it's a very exciting field, and there's a lot of very good jobs in that area if that's something that interests you.
So thank you all for coming. We appreciated your time and especially your participation.